Hello everyone, I'm very glad to introduce our recent work on GCN-RL circuit designer, transferable transistor sizing with graph neural networks and reinforcement learning. My name is Hanrui Wang, and I'm a PhD student at MIT. Recently, artificial intelligence is witnessing rapid progresses and shows promising results in the EDA area because of its two merits. First, the inference of a model is very fast and can be accelerated by GPUs and accelerators. Secondly, the models are very accurate because they are data-driven. With enough data, the performance of AI models can exceed the traditional methods. It also enables continuous learning to make full use of the newly obtained data. AI models are already used in many EDA problems, including physical design and manufacture, circuit design, and system-level modeling and optimization. In GCN-RL circuit designer, we focus on the analog IC design problem because it is highly labor-intensive, requiring manual schematic design, transistor sizing, and layout design. To make things worse, the porting of analog IC between technology nodes also requires huge manual efforts and large overhead. To this end, we propose GCN-RL circuit designer using AI techniques to make analog IC design more efficient. We target at the challenging transistor sizing problem, which has large design space and complex performance trade-offs. We leverage the graph convolutional neural networks to involve topology information into the optimization loop, inspired by the fact that circuit topology is a graph. Transfer learning between technology nodes and different topologies are also explored to reduce the design porting overhead. GCN is short for graph convolutional neural networks. In one GCN layer, each node of the graph aggregates the features from neighboring nodes. The more GCN layers, the larger the receptive field. For example, in layer 0, the red node only has its own features. After GCN layer 1, it has information from its neighbors. After GCN layer 2, it has information from neighbors of neighbors. In GCN-RL framework, we firstly have a target circuit and a simulator as the environment. One optimization iteration contains 6 steps. In step 1, the environment embeds the circuit topology into a graph, whose nodes are circuit components and edges are wires. Step 2, the environment generates a state vector for each component and sends the graph with state vectors to the reinforcement learning agent. Step 3, the RL agent processes the graph and state vectors and generates the sizes for each node. The environment refines the sizes to meet circuit design requirements, such as transistor matching. Step 5, the simulator simulates the circuit with the generated sizes. In the last step, a reward value is calculated and fed to the RL agent to update policy. After many iterations, we get sizes with a high form value and also a trained RL agent. Then, to perform knowledge transfer, we can inherit the trained RL agent to design circuit in other technology nodes and topologies. We apply the actor critique algorithm as the RL agent. The actor generates the actions. The critique estimates the reward of the actions and guides the actor to generate actions with high rewards. For the actor and critique, we use GCN as the models. Here, we show the architecture for the actor GCN model. The actor takes a graph and states on each node as the inputs. Then, in the first GCN layer, we multiply the input features with the same weight matrix for each node and get hidden features. And then, we accumulate hidden features of a node with its neighbors to get its aggregated features. This process is performed simultaneously on all nodes, so we get all aggregated features. Then, multiple GCN layers are stacked together. Each has one FC and one aggregation operation. After several GCN layers, each node can have a large receptive field. After the last GCN layer, we apply a unique FC layer for each node and output the sizes for the corresponding circuit component. The critique model is similar to the actor model, but its last layer outputs the estimated form values. Our GCN-RL framework enables knowledge transfer since the knowledge of how to perform transistor sizing is stored in the weights of the agent. So we can apply the trained agent directly on other technology nodes or topologies. By contrast, Bayesian optimization and evolutionary search cannot support knowledge transfer Because BO has a fixed output space, ES keeps good samples in its population without summarizing the knowledge. We evaluate the performance of a GCN-RL on 4 circuits, including a 2-stage transimpedance amplifier, a 2-stage voltage amplifier, a 3-stage transimpedance amplifier, and a low dropout regulator. We use the weighted sum of several normalized performance metrics, such as bandwidth, power, and gain, as a figure of merits, and compare our performance with multiple baseline algorithms, including human expert design, random search, evolutionary search, Bayesian optimization, MACE, which is a multi-objective BO, and also with NGRL, which is reinforced learning without GCN. The experiments show that GCN-RL consistently achieves the highest form values with small variance. Here are the learning curves on 2-stage voltage amplifier and LDO regulator. GCN-RL is in the red curves. The results show that besides high form value, the GCN-RL also has the fastest convergence speed. Here we show the knowledge transfer between technology nodes on 3-stage transimpedance amplifier. The agent is trained on 180 nanometers and transferred to 130 nanometers and 250 nanometers. GCN-RL in the red curve can achieve much higher form values after only 200 steps. We also experiment on transfer learning between 2-stage and 3-stage transimpedance amplifiers. The red curve is transfer with graph information, blue curve is transfer without graph information, and yellow curve is no transfer. We can see that transfer learning with graph information achieves the highest form values. Transfer without graph information is very close to no transfer, showing that graph information is critical to transfer learning between topologies. To sum up, GCN-RL circuit designer leverages AI techniques in the EDA problem transistor sizing and gets better performance with less human labor. It consistently achieves highest form values and enables transfer learning between different technology nodes and topologies. For more information, please visit our website at gcnrl.mit.edu. Thank you very much for listening and welcome to my online Q&A session on Friday, July 24th, 2 p.m. to 3 p.m. Pacific time.